What's up, guys? Welcome back to Organic Chemistry Who. So today we're going to talk about a different topic. I really apologize that I haven't been, publishing or posting any videos in the past few days because I've been, quite busy doing my my homework and studying for common exams. But today I'm going to bring you something different, a little bit. It's quite simple, but it's kind of like a really interesting topic to look at. So suppose you have a plane over here, and then the plane is frictionless, and let's say that you have a huge mass over here, right? You have a huge mass, and suppose it has 100 kilograms. It's a mass of 100 kilograms, and then you're going to connect it to a sequence of masses, right? So like each time you're going to connect it to a sequence of masses, and each of them is half of the previous one, right? So this one should be 50 kilograms. And then we keep on doing that. So the next one should be 25 kilograms, okay? And so on. And this continues to infinity. So like this does never end, right? Okay? So you may be thinking, well, do we have infinite mass? Not necessarily, but we do have an infinite amount of boxes connected to each other. Now, for simplicity, suppose that the tension in between the strings, right, is negligible, right, and they're of negligible mass. And for this part of the problem, suppose there's no friction, no resistance of any type, right? And what we want to find, suppose we want to find, right, what's going to be the force that you need, right? Suppose you want to like pull this. So you want to pull this way. And you want to pull it a specific force so that you accelerate it, suppose you want to accelerate it to 9.8 meters per second squared, the value of gravity, even though we're doing it in the horizontal direction. Suppose you want to accelerate this system to 9.8 meters per second squared, right? Now, how are we going to approach this problem? Of course, we have to use Newton's second law, right? So we have that the sum of the forces is equal to the mass of the system, right, times acceleration of the system, right? We're considering the entire system as a whole. All right, so we want to find what's that force. I mean, we already kind of know the mass. We already know the acceleration, but we have to kind of, derive or just like think about what's going to be a formula for the sequence of the masses that starts at 100 kilograms and continues on to infinity, right? Each time, taking half of the mass, right? So this is an example of an infinite series, right? Because, well, this is going to be a sequence that's going to be represented by, 1 over 2 to the power of n, right? Because every time you're decreasing the mass by a half. So like at 0, right? At 0, we're going to have 100 kilograms. So this should be actually 100 on the top. Because if you plug in n equals 0, 2 to the 0 is 1, and we have 100. So that's for the first block. For the second block, should give you 2 to the n, which is going to be n equal 1, because this is n0. So this is n1, so that will be 100 over 2, which is 50 kilograms. So that's consistent, and that will be the sequence for our masses. Now, but we want to find the total mass, right? We want to find the mass of the system. And well, the mass of the system is actually the sum of all the masses, right, from here to infinity. So we have to actually do the sum from n equals 0 to infinity, right, of this sequence of masses, 100 divided by 2 to the power of n, okay? And if you recognize this, this is actually a geometric series, okay? And how does a geometric series look like? Well, it's something like this, look. So a geometric series could be either in the form of, the sum from n equals 1 to infinity of some value a, right, some constant a, times r to the power of n minus 1, right? And if we evaluate this series, this will be a, right? And then multiply by r to the power of your initial value, which is 1. 1 minus 1 is 0, so it's just 1. Now the second term will be n equals 2, right? So a multiplied by r, and then 2 minus 1 is 1. So, and then we keep doing that. R plus AR squared plus AR cubed, and so on, to infinity, right? Now, let's try to find a way, okay, to find the actual sum over here, okay, from scratch. So if we know that this is the sum, right, this is the sum Sn, okay, which equals to that, we could kind of determine that this is actually convergent. But it's only restricted to specific values of r, and we're going to see why. Okay, so now suppose that if Sn, okay, Sn equals a plus ar squared plus dot plus a r to the power of n minus 1, okay, and then let's say that we want to multiply, okay, just for this mathematical approach that we're going to derive the formula, let's multiply everything by r, right? So multiply everything by r. So we got that Sn times r equals to ar plus ar squared plus dot plus a, and then r to the n minus 1 times r is r to the n, ar to the n, okay? Now, from the proof, right, we're going to subtract Sn from this. So like Sn minus this, right? So let's do Sn minus Snr. And let's see what happens. So if we do that, if you think about it, if this is Sn over here, right, and this is Snr, right, we're subtracting this, we see that we have a lot of common terms in between. Actually, an infinite amount of common terms. But the only not so common terms are a, right? So if we actually do this, this should be a, right? So for Sn should be a plus, right? All of this will cancel out, we subtract this. And then we have plus ar to the n minus 1, right? Ar to the n minus 1, so plus. And then we're going to subtract, right? We're going to subtract all of this, and then we're going to end up having ar to the n. So look at that. Oh, by the way, this one cancels out because over here, right before ar to the n, we have ar to the n minus 1. So that actually cancels out. And we're only left with the first and last, right? A minus ar to the n. And over here, we could factor out Sn to find the actual sum. So Sn 1 minus r equals to a minus a times r to the power of n. We divide by 1 minus r on both sides, so Sn equals a minus a times r to the n, all of that divided by 1 minus r. Now, we have to analyze this carefully, right? So if we use the nth term test over here, so if we take the limit as Sn, right, of Sn as n approaches infinity, okay, we're basically taking the limit of this over here, a minus a times r to the n divided by 1 minus r as n approaches infinity. Now, you know that if you raise a number, a whole number, greater than 1 to the power of whatever it is, okay, to the power of infinity, you're going to get infinity, right? So this is going to be infinity, so let's write it over here. So Sn approaches infinity if, right, if the absolute value of r, okay, will be less than, okay, or equal to 1. Well, I'm sorry, no, greater than 1. Yeah, because if it's greater than 1, suppose it's just 1, not 1.1, right, or 2. If you raise this to the power of infinity, it will give you negative infinity, so it diverges. So that means it does not converge to some value, so it diverges. And then Sn, okay, approaches to some value if the absolute value of r is actually less than or equal to 1, okay? Because if it's less than that, okay, that would just approach 0, right? Because it will just be a fraction at infinity. So this term goes away, it goes to 0 at infinity, and what we're left with is Sn approaches a divided by 1 minus r. So this is the convergence of a geometric series. This geometric series, okay, is actually evaluated with this expression over here, a minus a divided by 1 minus r. All right, so we can actually find the mass, okay, from the infinite amount of blocks that we have, and let's see what happens. So now that we know how to find this geometric series, okay, the value of the geometric series here, we know that the mass of the system will be equal to a divided by 1 minus r. And A in this case is 100. So we're going to have 100 divided by 1 minus R, in which case will be 1/2, right? This will be the same as the sum of 100 times 1/2 to the power of n. Because 1 to the power of n is just 1, right? 1 to the power of anything is just 1, except for like, yeah, anything, really, even 0. Okay, so that would be minus 1/2. And 1 minus 1/2 is 1/2. You bring it up, you get 200 kilograms. So this is the actual mass of this system, even though you have an infinite amount of blocks, right? It's kind of like a weird concept, but it's interesting. So now we can actually find the force. So the sum of the forces of the system is equal to, right, the mass of the system times the acceleration of the system, and that's equal to 200 times 9.8 meters per second squared, and that should give you 16, right? That's going to be 9 times 2, 16, 8 times 2, 16 as well. So that would be 1660, right, newtons. Okay, so this will be the, oh actually no, I'm sorry, this is 1860, there you go, 1860 newtons. So this will be the force required so that when you pull this system, okay, you can accelerate it at 9.8 meters per second squared. All right, so that's a pretty cool, cool idea, having a infinite amount of blocks. And even though you have an infinite amount of blocks, you have a finite amount of mass. So that's pretty cool. Okay, thanks for watching. I hope you liked this video, and I'll see you next time. Please subscribe and share it with your friends.